So chapter 1, section 4 expands on the idea of exponents in a very specific area known as scientific notation. This is where numbers oftentimes in science wind up so big or so infinitesimally small that it's difficult to use a standard way of writing a number. So this isn't that big a number, 29 million. But what if this is 29 trillion or even bigger if you're measuring, say, the distance from one galaxy to the next, maybe in miles or in kilometers or something like that. Or you're measuring, say, some very small number like this one. Maybe it's the distance across the nucleus of an atom, in which case you're going to measure it in meters or centimeters or whatever, and you have to then you have an incredibly long set of zeros following the decimal point, and then finally a number. And what happens with that is that the zeros so dominate the dialogue that it's almost impossible to handle the information. And so scientific notation came along in order to allow really big numbers to be written in ways that are a little bit easier to manipulate, especially if you're going to combine these really big numbers and you're going to multiply, add, divide, subtract, whatever you're going to do. You start messing with these huge numbers. It's much better to have them simplified in scientific notation so that you can multiply or divide easily by using the rules from the exponents from the chapter 1, section 3 that we just looked at. Now, that being said, I'll let you know this up front. We will do a little bit of scientific notation. You do have to know how to do it. We're not going to spend an enormous amount of time on it because, to be honest with you, the book only comes back to this idea a couple of times. Now, the one part about it that is good is that it forces you to practice your exponent rules of dividing or multiplying exponents, what to do when you have common terms with exponents and you're going to combine them. And so there's good practice there. So I don't want to spend a lot of time with this, but you will have to on the test be able to take a number like 29 million and write it in scientific notation, or a number like this, 0.00035, and write it in scientific notation. You have to do that on the exam, and so I want to show you how to do that here. And then I'll show you one other problem where we'll multiply and divide a series of numbers that are written in scientific notation, and show how scientific notation allows us to more quickly simplify fairly complicated looking terms. And then that'll be about what we cover here. There's some homework from this section. You should definitely practice doing the scientific notation. Now, here's the deal. Scientific notation is where you take a really large number or a very small number, and what we do is we standardize it. The scientific notation is a way of standardizing the way of writing that number as a decimal point and a power of 10. So the way this works is you find the leading non-zero leading number, 2, or in this case of the decimal point, 3, and that becomes the first number in scientific notation. 3, 2, the first number. Then, so just follow the process here. Right after that lead number, you put a decimal point. Right there, decimal point. And then the next number is any number that follows that lead number. It could be a 0 even, in which case you'd write 2.0. Or 3.0, but in this case it's a 9, so we write 2.9. And then you write out whatever number until we get to a 0. So in this case, 3.65 in this particular case. But in this one here, 29 million, you write 2.9 times 10. That's the next thing, times 10. And now we're going to count, okay? You ready to count? This is a counting exercise. We start here and we start counting until we get back here. 1, 2, 3, 4, 5, 6, 7. Now, if the number's big, then we're going to have a positive exponent. If the number's small, smaller than 1, we're going to have a negative exponent. See that? So, in this case, this number is less than 1, 0.000 and so forth. We're going to move the decimal point now this way. 1, 2, 3, 4. So there's a decimal point here. We don't write it when we write 29 million, but there's an implied one that's there. We have to write it on this one, of course. It wouldn't make any sense without it. But there's a decimal point here, and we're going to count from the position just past the first non-zero number. So 3. We're going to count right there between the 3 and the 5. We're going to count 1, 2, 3, 4. If it's a small number, then we're going to need a negative exponent. Okay? If it's a big number, we're going to need a positive exponent. All right, so let's see it with this one here. We have 365 million, all right? So the first thing we're going to write down is the lead number we find here, which is the number 3. Then the next thing we're going to do is put a decimal point. That's step 2. Decimal point, right there. Got it? 3 decimal point. Then we're going to go find all the, if there's a 0, we write 0.0. If there's not, we're going to write whatever numbers there are until we get to the 0. So 6, 5, and then, so now we're all the non-zeros have been written down. Now we're going to do times 10. So now we're left with counting. We're going to count now. Ready? So we're going to start here between the 3 and the 6. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 spaces there. So 8 places we move that decimal point. Now let's try it down here with the numbers less than 0. We're going to find the first non-zero number, 2. Now if it was just 2 and nothing after, we write 2.0 times. But what we have here is we have a non-zero after, so that's 2 point, and then we're going to write all of those terms, 8, 3. Okay, so now we have all the non-zero terms written down. The next step is write times 10, times 10. Now all we got left is the multiplying factor. Now this number is less than 0, so this is going to be a negative. It's going to be a negative, right? Okay, so here we go. So we're going to count from that spot between the first or lead non-zero number 2 and that 8 there, right there. We're going to count 1, 2, 3, 4, 5, 6, 7. 7 times. That's minus 7. Minus 7. That's how many times, 7 times, that's how many times we move that decimal point this way in order to write it in scientific notation. So the final way of writing this decimal as a scientific notation is 2.83 times 10 to the minus 7. All right, now let's talk about combining let's talk about combining some terms like this. Let's suppose we have the following, and I'll use an example from the book. Let's suppose we have 0.000064. And that's one term. And we're going to multiply that times 24 billion. All right? And then we're going to divide all this by 400 million. And then we're going to divide it additionally by this decimal point, 0.00, 1, 2, 3, 4, 5, 6, 7, 1, 2, something like that. So that's a mess. But if we write it in scientific notation, we can simplify the mess just a little bit. So let's see if we can't do that. So this first term we're going to write as 6.4 times 10. And now the only question is what goes here. Now notice it's less than 1, so we're going to put a negative sign there. And now we're going to count between the 6 and the 4. 1, 2, 3, 4, 5, 6. 6 times from the 6.4 till we get there. And this one, we're going to write it as 2.4 times 10. Okay, first step. Find the leading non-zero number. Write that number down. Put a decimal point. Write any other non-zero numbers so you run out of those. If there isn't anything but zeros out there, I would put a 2.0 in that case, just so someone knows you got the placeholder there and all that. But usually in this case, like 24, we're going to write 2.4. Usually you're going to have something other than zero behind it. A lot of times, especially in the scientific world, it's odd to have a huge number but only one non-zero number in it. It's very uncommon for that to happen. It could, but it doesn't happen too often. So in this case, we're going to count now how many to get from the 2.4 till we get to this decimal point. It's not written here, but it's implied. Because we don't write decimal points behind these really huge numbers with a bunch of leading or trailing zeros. But it's implied. There's an implied decimal point there, so we're going to count between 2.4 to get down there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times. Then we're going to divide all this. And we're going to write this as 4. Now here's an example, 4.0 times 10. And my preference is to include that 0.0. Other people don't. This book doesn't. I just like it because if you don't, sometimes people think maybe you forgot to write something down. So I kind of like having the 4.0 there. If you don't have any other, that lets the person know you didn't forget it. You didn't leave it out. You know it's zeros after that 4. The book has it written like this. Either way is, I think, fine, but I kind of like having the placeholder there. It informs the person reading your scientific material that you do know that the 4 is not the only digit. It was 4 with trailing zeros, and you've included all the information there. Okay, now to what power here? We start here and count 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8th power times. And then again, we have 1.2 times 10. Only it's less than 1, so we're going to have a negative exponent. So let's count between the 1 and the 2. 1, 2, 3, 4, 5, 6, 7, 8. 8 times. And so there we have it. So now, the way this works out, we have 10 to the 10th, 10 to the minus 6. If we combine those two, we'll have 10 to the 4th. And down here we have 8 and minus 8. That's 10 to the 0th, which is 1. And then we have 6.4 times 2.4 times 4.0 times 1.2. And so by the time we cancel all these out, let's see, 4 goes into 64 times. 16 times, so that's 1.6. And 12 goes into, 1.2 goes into 2.4 2 times, so that's 2.0. So by the time this is all said and done, it looks like we have 3.2 times 10 to the 4th. And that is a much simpler final answer than what is written in the original fraction. So that's how using scientific notation can simplify things pretty well. Now, by the way, if you don't just see that immediately, you're free to take a calculator and multiply 6.4 times 2.4 divided by 4 divided by 1.2, which you'll get 3.2, and then you have this 10 to the 4th still left out here. And so that's the way you get that final answer. All right, so practice some of these. If you don't practice, I think this will be hard on an exam. But if you practice them, I think these are give-me questions, ones that you can easily get just by paying attention. There's just a few principles you have to follow that I've shown here in the video, a few basic approach every time you see one of these. That if you just do that every time, just follow the pattern, I think you'll be fine. All right, that's Chapter 1, Section 4.